This is part 2 of Unit 6, Lesson 3. I forget the name of the lesson. Area accumulation. I do believe it is. It is accumulation functions in general. Sorry about that. Okay, so we're going to continue with our idea. We kind of started it in the last part, talking about what we do by altering the limits of integration. And so we started with this example 3 where we talked about our area going from k to x. So now what if we change that? And in this case, our k was 0. And now what we're going to do in this example is we're going to change our k to 3. So now you can see, whoops, our lower limit here is 3. So how does that change things? So where is the 0? The 0 is now going to be at 3. And how we can recognize that is the idea that that's where we're starting from. That's our starting value. And we can think of g of 0 in this way. So g of 0, and let me pull the graph up here for a second. In order to get 0, what we have to do is we have to go backwards here. So we're going to take our starting value and we're going to have to subtract from it going backwards. So we have to take off how much area that is added on here to get to 0. So this area here has to go away. So that's how we're going to define that here. So g of 0 is going to be the integral from 3 to 0 of f of t dt minus the integral from 0 to 3 of f of t dt. And what we do when we get that is we get the 0 is going to be at x equals 3. And the value of that is going to be taking off that area, which is going to be, let me just erase this so it's out of the way, is going to be negative 4.5. So we're going to take back. We have to move backwards, so that's in a negative direction. And we have to get rid of this area here. And that area at 3 was 4.5, so it'll be negative 4.5 is where we're at now. Okay, so what is the domain? So since we can go backwards, and remember that its derivative of g is f of t, and f of t is defined completely from our original a to b, which was 0 to 10. So that is not going to change any. So I am going to skip D. I don't want to get into that at this point. We're going to talk about that in a later lesson. So what is the maximum value of G? And that maximum value is going to be 7.5. Okay, to show how I got the maximum value of 7.5, I'm going to make another table here, and I'm going to start at 3 and go from there. So here's my g of x. So at 3, I'm at 0 because I haven't moved. Now that's my starting point, so I have no area under that part. And then when I go to 4, that's supposed to be a 4, not a y. So when I go to 4, and let me just make this a little smaller so we can see the graph. Okay, that'll work. What I'm going to do is I'm just looking now at that one little trapezoid right there, which is right here from 3 to 4. So that little trapezoid. And the area of that trapezoid, excuse me, is 3.5. And then when I go to 5, I'm going to add on the next little trapezoid right there. And that gives me, at 5, I'm at 6.5. And at 6, moving over, I have that little triangle there. So then at 6, I'm at 7.5. And then at 7, I'm below the x-axis. So now I'm going to start subtracting off areas. So I subtract off that little triangle there. So then I'm at 7, because we figured out before that triangle, we were estimating that one to be about 1/2. And then the next one, the trapezoid at 8, I'm going to subtract off that area. So that is going to give me 4.5. And then the area of the next little triangle there, actually I have another trapezoid there, is going to put me at 2.75. And then finally that last little triangle is going to, which is 1.5, is going to put me at 1.5 at 10. So I'm not going to give away what's going on here, but you'll see it when we get to the point where we graph it. So that's how I know that my maximum value is 7.5, because in my table of values where my function is defined, that is the maximum value that I have. So where will it occur? It occurs where x equals 6. So what is the range? And we can see, really, it looks like 0 to 7.5, but don't forget, we can work backwards, and we know that at 0, our y value is negative 4.5. So our range is going to be from negative 4.5 to 7.5. And we're going to sketch the graph. And so let me move up here, and I'm not going to use green. Let me just erase all of this in here, but not my green graph. I'm going to use the reddish color there, and I'm going to plot all these points. Okay, so there's the graph, and now let's talk about it a little bit. Okay, so we sketched it, so let's talk about it a little bit. Describe the relationship between all f of x from the definite integral from k to x of f of t dt as k takes on different values. So what do you notice about the relationship between the green graph and the reddish graph? And what I hope you notice is they have the same shape, that we actually have a vertical shift here, and it's a change of 4.5 units down. And that'll be the same anywhere you look here, that this has been shifted down 4.5 units. So describe the relationship. We have a vertical shift of one graph to the other. So let me use that's not a good color to write with. Let me use blue. Okay, so what we have is all f of x graphs are vertical shifts of each other. Okay, what point must lie on the graph of any of these given family members, and why? And that point is going to be k comma 0. And the reason for that is that when k is our lower bound, sorry, I'm having trouble with this pen. So when k is the lower bound, our first area is going to be the area from k to k is going to be 0. Let me write that a little better. From k to k is 0. And we did that in both examples. So if you look up here, when we went from 0 to 0 in the green graph, our area was 0. And then when we went from negative or 3 to 3, our area was 0, because we really don't have any width, so we have no area under the curve at that point. Okay, so next question. As k takes on different values, the functions of f of x from k to x of f of t dt graph, as we want to think of them as vertical transformations of one another, each containing a particular point. And of course, that point is just what we were talking about which is k comma 0, even though the lower bound has changed. That's a really bad question, so I don't even think we really need to answer it. So that's true no matter what. So even though we've changed the lower bound, that point, because that's going to be like our initial value, there is going to be no area under that curve. Okay, so next example. Shown below is the graph of the derivative of f for some function, capital F. And we're going to assume that f of negative 3 equals negative 8. So we already have a value here on our graph. And so let me mark it here. So here we know that f of negative 3 equals negative 8. So we're asked to find f of 2. So let me just point something out here, that as we move to the right this way, we're going to add area. And we did this a little bit in the last example. And as we move to the left, we're going to subtract area. And I did that to find a g of 0 in the last problem. That is the messiest looking word, subtract, ever. I don't know why for this lesson, my computer is glitching. Okay, so if we're looking for f of 2, what we're going to have is, we're starting here at negative 8. That's our starting value. That's how we're going to look at that, as our initial value. So this is our initial value. So we're going to add to that. So f of positive 2 is going to be that negative 8 there. And then we're going to add to it all these other areas till we get up to 2. So we have an area that's labeled as 10 square units, and then another one that's labeled as 26 square units, for a total area of 28 square units. And then we go f of 6. What we're going to see is we can take our 28 that we already have, and then we are going to have to subtract off that 8 that's below the x-axis, and then we can add on the 14. So we get a total area of 34 units. And then f of negative 5, so now we're back to our starting value here of negative 8, but since we're moving to the left this way, we're going to subtract off that 18 units. So we get a total area of negative 26 square units. Okay, so for part D, since the area under f is positive on the interval from negative 3 to negative 1, we know that the graph of f must be, and just like before, because remember this is its derivative, if we have a positive derivative, that means the function itself, and we're going to start calling it the antiderivative, is going to be increasing on that interval. That has not changed any, just because we're changing our terminology, and instead of looking at a derivative, we're looking at an area or an antiderivative now. Since the area under f accumulates at an increasing rate, we know that the graph of f must be concave up, because we're talking about a change in a rate of change. So if we have a positive rate of change changing, that is our second derivative. So when that's positive, that means that we are concave up in that same area. So the area under little f from negative 1 to 2 accumulates at a decreasing rate. So if you look at our graph, so when we're from negative 1 to 2, we can see that the area is accumulating at a decreasing rate. So from negative 1 to 2 here, it's accumulating at a decreasing rate. It's kind of slowing down a little bit in its accumulation. So this is accumulates at a decreasing rate. So f must be concave down on that section. On negative 1 to 2. So we're supposed to sketch this knowing these things. So let's go ahead and do that. Well, we do have the points that we just found, and we can fill in the rest of these points. So at negative 5, we already know that one. That was given above. That's negative 26. At negative 3, we have that. That's our initial value that we were given. So annoying. That's negative 8. Negative 1, we didn't figure that out, but we can see from our graph above that, let me just make this smaller so we can see the graph and the table. At negative 1, we are going to be taking our initial value here at negative 3, and then we're going to add to that the 10. So we have negative 8 plus 10, so we get 2. And then f of 2, we already did above, so that's our 28. F of 4, we did not do, but what we're going to do is we're going to take our f of 2, and again, we're going to subtract off that 8, so we get 20, and then we already figured out f of 6, and that was 34. So let's go ahead and sketch that. And what we're going to have, okay, so let me center this a little bit and sketch the graph, and then we can discuss it. Okay, so here's what the graph kind of looks like. You can see where we are concave down, up right along there, and then concave down from negative 1 to 2. Hang on, I drew that backwards. We need to be concave up from negative 3 to negative 1, and then I didn't flip that over very well. I'm sorry. Let me fix that. So we are going to be like this. Let me get rid of that little piece there. Sorry, I misspoke you there. So it's going to be like this, and then we're concave down to here, and then concave up, and then we flip over. There we go. That's not too bad. Okay, so talking about some important features, you can see we're going to have a horizontal tangent line at those points. My zero is a little off there, I apologize. And then, of course, then that makes this, we have a relative max. And we have a relative min. We have an inflection point here because that's where it flips over. I don't know why I'm writing reflection. We have an inflection point at that stage. Okay, so next example. So our last example then is a calculus-based justification for the graph of g prime equal to f. In differential calculus, we use the derivative f prime to discuss properties of f. In integral calculus, is what we're studying now, beginning to study, we need to reverse our thinking. Our new goal is to use a derivative function to talk about antiderivatives, which is very similar, as I was saying during the last example. In the example below, we say that g is the antiderivative of f. So we're going to summarize all these relationships right now in this example. So we're given the graph of f, and we're going to let g of x equal the integral from 0 to x of f of t dt. So f is positive on the interval from 0 to 8. And just like before, remember, f is the derivative of g, so that means that if the derivative is positive, then the function is increasing on that interval, so it's increasing. And f changes signs at where it goes from positive to negative. And at this point, it's going to be at the end of our defined interval. So we're kind of cheating a little bit because it's happening at the end of our defined interval, but we're going to put at x equals 0, it changes sign. So g, if this were to continue, we could say that g has a relative maximum since f goes from positive to negative. We can see it on the graph, even though it's not included in the originally defined domain that we have here, our interval. Well, I guess technically that isn't our interval. It just says it is positive in that interval. So it is continuing here, so we can talk about it. So I was misreading what was written there. So yeah, it does change signs there. It actually changes signs before 0, but remember g is defined from 0 to x. So we're going forward, not going backwards from 0. Okay, so part C, the graph of g is decreasing where f is negative. For values of, that's going to be anything greater than 8. So we can put x is greater than 8. So the graph of f is increasing from, now we're talking about f now, so it's increasing here where it has a positive slope. So that's from 0 to 4. So g of x has to be concave up because we're going to have a positive second derivative. So it's concave up. So this hasn't changed from how we discussed it before. So then the graph of g is concave down where f is decreasing. So it's going to be negative. So we'll have it, its slope will be negative. So where f is decreasing. For values, and that would be for anything greater than 4. Okay, so the graph of f has a maximum at 4, and so g of x has an inflection point. Oops, the and's already there. And how we know that is we have a horizontal tangent line here, and this graph is going from increasing to decreasing slope. Okay, so then for the end, this is a summary of our justification. So we know when the derivative, and this is just what we were doing before, when the derivative is positive, the antiderivative is going to be increasing. When the derivative is negative, the antiderivative is decreasing. And when that derivative is increasing itself, we have a concave up antiderivative. And if the derivative is decreasing, we will be concave down. And where we change the sign, that is where our extrema is going to be located. So that's going to summarize and put together what we've done before and connect it to what we're now calling the antiderivative. I will take any questions in class tomorrow.